start from where we left. Finally, you will have an answer of how to search this mysterious X17 particle. I'm sure you didn't sleep last night thinking to the X17. And so we saw this interesting anomaly from the experiment Atomkey, and we also saw that this can be explained with dark photon-like particles with masses of order of 17 MeV. And we also saw that there is still some available parameter space to search for this particle. It is given by the fact that this region of the parameter space produces particles that are too light for the searcher colliders, too feebly interacting to the standard model to be searched a thin target experiment, but also too short-lived to be searched at bin dumps, because they will be produced and decay within the dump itself and not be detected. So we need really some new idea to search for this particle, and what we will need really will be some very precise probe, since for this time we know what is the mass of a candidate. All the other searches that I have discussed up to now, there were no particular hint about the mass of the particle we're searching, apart the range 1 MeV, 1 GeV, which were referring for the lighter matter particles. And this may come from this process here, which is the resonant annihilation of an electron and positron pair into an X17 particle, or a dark photon with a 17 MeV mass. So if you have a positron beam, for example, that impinges on a fixed target, so that the square root of S is 17 MeV, you will achieve the possibility to produce X17 via this process, which has a really enhanced cross-section and a very narrow cross-section, because you're talking of a resonance with a small width, because you know it depends, talking about the visible scenario, so the width will so depend on epsilon square, so very narrow particle. And so we have a process that maybe we can try to use so to tune, for example, the energy of a positron beam to produce a particle this way. This process is interesting not only for the fact that it is narrow in terms of cross-section, so we need a very specific energy of a beam to achieve it, but also because at a better scaling with respect to alpha electromagnetic, for example, with respect to the A prime Strahlung that HPS uses and we so uses for research. So we need a positron beam which has an energy of order should be 390 MeV. So not much energy, and this can be achieved with a very small accelerator. You will not need a large collider. And this is what was trying to do the Padme experiment. So this is a very small experiment in Italy, at the Laboratorio Nazionale di Frascati, and the Padme experiment actually was already taking data when the X17 anomaly was observed, but they were using a technique to search for invisible decay of dark photon. But when they saw this anomaly, they decided to modify a bit the setup of their experiment and move to a search for a visible decay with a tuned beam energy, so to produce this positron beam, this X17 particle via this resonant annihilation. So the setup you see here, this shape, is due to the fact that in principle there was a magnetic field here to bend particles to search for the previous strategy used by Padme, but now they're not using any magnetic field. They simply have a vacuum tube, an active target which measures the position of the impinging of the particles. We'll see why later. And you have this beam, positron beam, impinge on the target. You hope to produce electron-positron pair via this process, and then you measure in an electromagnetic calorimeter the two particles in a similar manner of what HPS did. So this is a photograph of an experiment, just to give you an idea, really with small scale of what we are talking about. This is an experiment apart obviously from the beam, the detector can stay in a small room. And what the principle of the measurement? So we saw that we can produce, if it exists, this particle via this process. But then there are many processes of the standard model that result in annihilation, that from the annihilation of an electron-positron pair produce an electron-positron pair. Simple annihilation where you mediate with a standard model photon result in an electron-positron pair. So if you just measure at one beam energy and you count the number of annihilation that you have, you simply will see a number due to the standard model processes. But what we thought to do was to basically perform a scan in energy around what is the mass of the X17 particle, or more precisely, what is the lab frame energy of a beam that in the center of mass frame reproduces the square root of S, which is the mass of X17 particle. If you do so, what to expect is that at some point while you scan and you change the energy of the beam, going from, for example, we started from 350 and went up to 400, you expect to see at certain point an increase in the number of counts due to the fact that you start to achieve, to be possible to produce dark photon X17 via the resonant annihilation. Of course, we are talking of an increase of count which is order of percent with respect to the standard model, let's say background, the normal annihilation. So really need to control in a precise way your detector, and you hope the detectors to be very stable. But here, for example, in the plot, you have the variation in the count from this resonant annihilation. So when you change the energy of a beam with two different strategies. So we thought to two strategies. Here is not the energy of the beam, actually is the square root of S, so the mass of the chi particles. So what you expect is to see an increase in the count from the dark matter process of up to an order of 100, which I remember is on top on a stable background, which is much great. So you have to keep it controlled. So this is their strategy, their idea to search for this particle, and this is the reach that they hope to achieve with a run of 10 to the 11 total positron on target. This is a conservative scenario where they do a scan which is a bit larger, so from 265 and 297 MeV lab frame energy of a beam, and to scan divide this range into 12 beams of the energy of a beam. Then they also thought of a more aggressive technique, aggressive scenario, so a bit more statistic, and most of all a narrower range around the X17 resonance, and a larger number of beams. So basically scanning this resonance with more precise, more fine beams. And you can see the reach expected sensitivity is what is enough to go from what is the result from Chloe here and an A64, which are the two experiments that up to now are constraining the X17 parameter space. And so they hope to close this window using this technique that will not exclude very large amount of parameter spaces, but will exclude the region which is of interest for this anomaly. So this is something a bit different from what usually done. They've taken the first data, and we are going on with the analysis, which is complicated. So maybe soon we will have an answer if this X17 is really a particle or just some nuclear anomaly. Okay, so this was the last thing I wanted to say for the theme targets before moving to the beam dump experiment, which will be the topic of this lecture main. And so the idea here is that, as I think is clear from the last lecture, is that for this thin target experiment, you need really to go up with intensity of the beam to be able to reach those regional parameter space where the coupling are very feeble. But you cannot do so. You cannot just increase, for example, the current of the beam, because on one side you will kill your detector with radiation. On the other side, the rate will be so high that you won't be able to trigger anymore. So in principle, you will need something allowing you to go up with the rate, but without having to save, to analyze a lot of events that at the end of the day are standard model events. For example, if you think of the invariant mass spectrum of HPS, just a large spectrum of standard model things on top of a small peak if it exists of a dark photon. So we need to filter somehow. And there is a physical way to do so, which is a beam dump experiment. So what you do? You have your beam, which can be beam of electrons or protons or whatever, and you make it impinge on a fixed target. So here everything, many things happens, shower, electromagnetic shower, hadronic shower, production of particles, we'll see later. And you may also produce, for example, dark matter particle. But then you put a shielding there to shield all what is coming from standard model, so muon, neutron, whatever. And after the shielding, you place a detector to see the signature for the interaction of such a particle from dark matter or the dark sector region. So in this way, basically, the intensity is being dumped on the dump itself, which can go up in current as much as you want and as you can, and you don't have a large rate on your detector. So basically what you are doing, if you think of a dark matter model, is basically producing like a direct search where you produce your dark matter wind and you make it impinge on your detector. So this is the basic idea. Usually the typical dimension length of this experiment is that you have your detector located at least order 10 meters behind the dump, but more commonly order of 100 meters. The beam energy varies from 10 to 100 GeV order of magnitude, and there are different possibilities. You may have decay volumes if you think that your particles from the dark sector may decay or not. You can vary the distance, the shielding, and so on. Before speaking of experiments themselves, I want to describe a bit more in detail what happens in a beam dump when, for example, you have an electron beam, high energy electron beam impinging on it. So as you know, what happens is that you produce an electromagnetic shower because your positron will irradiate a photon which may convert to electron-positron pair and so on. So in terms of what is the radiation length, you will see the number of particles increasing and therefore the developing of this shower of particles. And so inside your target, your beam dump, you have not only the particle of the beam, but many other particles that produce electrons, positrons, for example, but also photons and muons. And therefore, in order to really quantify how many particles are concurrent to the production, for example, like dark matter, we need to introduce a quantity that is called the track length or differential track length. This defines basically the average path that each particles within the shower do in an energy range which is between E and E plus T. So, for example, if you integrate between 0.2 and 0.3, this is a fraction of the energy of a particle within the shower with respect to the initial energy of the beam. You will integrate, you will get a number which is how long is the path on average that the particles within the shower do at that energy, so in that interval of energy. So, for example, this is the threshold track length for electron and positrons if you have an electron beam that impinges on a thin target, or thick target, sorry. So you can see that you have obviously a large track length for electron, but also many positrons, because as I said, you produce a lot of positrons in your shower, and so you have, in particular at the lower fraction of energy of the beam, a significant amount of positrons. So basically, what this means that a thick target experiment is not only allows you to go up with the intensity of the beam, but also that a single thick target event may be seen as many thin target events where you have different particles at different energy. And when you are interested in producing particles that are feebly interacting, that you really don't know, you want to explore different possibilities, this is maybe very, very, very helpful. So, for example, you can have access to different production processes, not only the A' Strahlung, that is considered mainly for the thin target, but also annihilation, where you have a production of a dark photon associated with a photon, but also the resonant annihilation that Padme itself was trying to use. So here, these processes, you have a cross-section. You see that there are differences depending on the mass of the kind. It's not very clear to see, but anyway, if the dark matter party candidate produced here at large mass, the energy, the cross-section is peaked at large energy, otherwise it's more flat. Here I have this cross-section, but depends on the fact that in the center of mass frame, the photon and dark photon go back to back, along with the, prefer to go along the direction of the beam. And here you have a bright Wigner, so the cross-section for a resonant production. You can see that also, apart from the shapes, also the scaling is different due to the Feynman diagrams that result from this production. So you have, in particular for alpha electromagnetic, alpha to the third, alpha to the second, and alpha for the resonant production, which means that this is where it is kinematic available, it is dominant. And we will see this in the result of the experiment. So to summarize, for example, if you want to know how many particles you produce via this resonant annihilation in a thick target electron experiment, what you need to do is just to take your track length of positrons and average it on the cross section, and then you get the number. So what this means? This means that a thick target experiment is doing for free a scan in the mass of the dark photon, for example, because if you have particles in the shower that goes from the initial energy of the beam to zero, basically, then you are scanning masses, energies, and then therefore masses in the center of mass frame that go from some maximum to a minimum. Obviously, this means also that the energy of a particle of a dark photon, for example, is bound to their mass, which is another important interesting thing. Okay, so first experiment of what I want to talk is a E137, which is a very old experiment running, I think, in the 80s, which was optimized not for dark photon search, dark matter search, but for axion-like particles. So anyway, particles that are thought to be long-lived and feebly interacting. This was an experiment performed at SLAC in the US, and they simply dumped 2 times 10 to the 20 electron on a beam dump at 20 GeV. The dump was basically a water-filled beam dump made of aluminium. And then the detector was on the side of a hill that acted as shielding. Then after a few hundred meters, you have your detector. So they expected basically ALPS particle to be produced here, travel through the shielding, and then decay in this region here. So they hope to see the decay product of the ALPS in a detector, which basically was a calorimeter made of plastic and lead, plus some tracker to define the direction, coming direction of the particle. They made the experiment in the 80s, they did not see any signal. So what what has been done in the last year, given the rise of interest of the theories of light dark matter, to reinterpret this null result in the theory of dark photons. So this has been done in the last year. Obviously, you can consider the production of dark photon given the electromagnetic shower produced inside the beam dump of E137. In this case, also, you can think of a long-lived dark photon that, exactly as in the ALP case, travel through the shielding and then decays in front of the detector, and you can see it. So reanalyzing, reinterpreting the result of E137 in this scenario, they were able to put constraints, and here you see the shape, typical shape that we saw in the last lectures regarding the beam dump experiment, and exclude a couple very low up to down to epsilon equal 10 to the minus 8. So here you have this shape, and now we can see from what it comes. So here the coupling is larger, so goes up, so you produce more dark matter particles, but the dark photon is short-lived, and therefore it decays inside the shielding. So if you had produced it, it had decayed inside the hill. You don't see the decay product, and this goes up in this direction, since if mass goes down, also the gamma of the particle at the same level of energy goes up, and so it leaves more. So you can see particles, larger coupling for small mass particles. On the other side, when you go down to a certain level in epsilon, you simply does not produce any more this dark photon, and then your sensitivity is limited. So in the same work where they realized this experiment, they also realized a series of earlier beam dump experiments, which are all in the same fashion. Basically, what changes are the energies, the statistics, the distances between the detector and the beam dump, the shielding, and so on. And we were able to put this limit, which are still today quite strong in the scenario of dark photon. But the experiment was interpreted also in the invisible scenario, because you don't need necessarily a decay to visible particle to detect dark matter, but you may think of the scattering of a dark matter particle inside your detector. And so also in this scenario, the experiment was realized, and it was considered for scattering inside the detector an elastic interaction with the electrons of the detector. The result, therefore, in a transfer of energy to an electron, an electromagnetic shower again inside your detector, and they placed the limit in the scenario. And you can see that even here the limits are quite interesting. This wheel shape here comes right from the resonant production. So this line here is due to the Bremsstrahlung production of dark photons. But here, what dominates is the production via resonant annihilation, because you're doing your scan in energy. And if you look at when it starts and when it finishes, the dominance of this process, here you have an energy which corresponds in square root of s, a mass which corresponds in lab frame energy of the experiment 20 GeV, which is the maximum energy of a beam. And this is 1 GeV, which is the threshold they adopted in the analysis to define if the signal may be a ALP signal. So this proves this experiment is very old, may be competitive still today for this parameter space. I have to say that this is a bit old and things have gone down a bit, and A64 in particular covered this region, but still, this is an interesting result. Okay, we move now to a future experiment, another beam dump experiment, that therefore has been optimized for this search. So, in particular for the search of dark photon in the invisible scenario, so searching the scattering of this particle. So, this experiment has been proposed at the Jefferson Lab. The idea is to use 11 GeV electron beam, impinging again on a beam dump which is made of water and aluminum. The detector will be much closer to the position of the dump with respect to A137, and there will be a dense passive shielding optimized to scan to stop all standard model particles, so we don't reach the detector, and still some overburden over the detector itself to shield part of cosmic rays and cosmic particles that may mimic a signal in your detector. The detector design is fairly simple. It's an electromagnetic calorimeter made of cesium iodide crystal, which, as we see, the idea was to get them from the Babar calorimeter, because Babar is no more used, and the crystals were basically free, at least at the first glance. So the electric volume is about half meter, so not really large. And then you have LED shielding that we see what it's useful for, and 2 layers of plastic scintillator that are used as active veto. So you want to veto all the particles that come from outside and can mimic dark matter signal. As I said, this experiment is at BDX, is at JLab as, for example, HPS. And it will exploit again the really high current that this accelerator can provide. So we are talking about 65 microamps in what is the whole A, which is the whole of Jefferson Lab, which hosts high intensity experiment. And this would allow to collect 10 to the 22 electrons on target in order of 1 year beam time, which is 100 times what we on 37 did. And also another interesting thing is that since the beam dump of the hole is here, so the detector will have to be placed on a new hole behind the beam dump. The hole still can operate with other experiments, provided that they don't degrade the beam too much, while the BDX experiment run parasitically. So basically you can operate the several experiments at the same time. And it was originally thought that this experiment, which is called Moller, which is running for several months without using degrading the beam, would be a good companion for BDX. So here I have a sketch of the new experimental hole, the BDX detector, which is underground because the beam dump itself, due to radiation concerns, is underground, and it will just be a simple hole with the detector. Here you have a more precise sketch of what is the beam dump of the whole A of Jefferson Lab, which is basically a tank of aluminum plates of different thickness filled with water that you need to cool down this target, because you're dumping there really an intense current, and therefore you will damage it if you don't cool it properly. So here you have the design and this 3D vision, but the important thing is that we know how it is done. This can be, for example, included into Monte Carlo simulation that perform the calculation of the production of dark photon, and so you can reasonably know what is your yield of dark matter particles when you make it impinge, when you make a beam impinge on it. So a bit more detail on the detector. It will be made of 800 crystals, cesium iodide, doped with thallium, which enhance the light yield of this crystal, which is to say how much light they produce at a given energy deposited, and will be arranged into modules, 8 modules, each 10 by 10 crystal. The crystals are quite long, and as I said, the idea was to reuse that one from Babar. There are thousands of that are not being used in many years, and so why not using them? They are quite big, 30 centimeter long, but here what you care is just to make some active volume to detect make impinge dark matter particles, detect the magnetic shower resulting from the interaction. why I told before the LED shielding inside between the Vito. This is basically to protect the Vito from the signal inside, because if you have an automatic shower produced by dark matter particle without any passive materials between the calorimeter and the Vito, it is highly probable that particles from the shower will hit the Vito, and then you are vetoing your event, your dark matter event itself. So, and in fact, the efficiency for the detection of such showers is order of 50%, is dominated by this effect of shower splashback to the veto counters. Here, for example, a signal registered from this cesium iodide crystals. They emit a lot of light, but you can see their emission after a particle has passed is quite long in time. So we have a long decay time. Therefore, these crystals are good for our purpose, because we don't expect to have a large rate of dark matter impinging of a detector, but for high rate uses may not be the right choice. Also, we checked how good can be the time resolution, because if you want to use a signal from Vito to reject event, you have to equalize in time your dark matter signal and the Vito signal, and we saw that you can achieve a resolution of order 5 nanosecond time, which is enough for the BDX requirements. Okay, so now a bit on the expected backgrounds of such an experiment. So everything that can produce something similar to a electromagnetic shower inside your detector, it's a possible background. And so that's the case for cosmic particles, such cosmic rays induced, particles induced by cosmic rays, so like neutrons and so on. We can maybe pass through the active shielding and interact with some of the crystals and deposit some amount of energy. So it's really complicated to evaluate this kind of background with simulation, because basically these are due to inefficiency maybe in the Vitos, really effects which are really complicated to include in simulations, and or really rare events, and therefore the only way was to measure it. So what was done, a prototype of a detector on a small scale was built. The prototype included basically all the elements of a big scale detector, and it was used for a cosmic ray measurement. It was left for a measure of some month, and then it was observed what are the position of energy resulting from this cosmic exposure after that you ask for the anti-coincidence of the two veto system, and then the result was extrapolated to the full scale of BDX detector. Here you have the spectra, and here the tail of this spectra after after asking for the anti-coincidence of the veto. And the result is that reasonably asking for a 350 eV threshold, you are background-free experiment from the point of view of cosmic particles. But there is another background which is not reducible, which is that one coming from the beam, because even if you have your shielding between the beam dump and the detector, you can rule out maybe all the standard model particles which are charged and neutrons. As you can see from this simulation here, they show the flux of particles depending on the distance from the dump, but for sure you cannot rule out neutrinos, and you are producing a lot of neutrinos because you are producing a lot of muons. Every once in a while you produce mesons which decays in neutrinos, and so you have to take into account this. An interesting thing about this the simulation of this experiment is that really you cannot, it's impossible to simulate the whole statistics, because 10 to the 22 electron target will be impossible for any computer or farm to simulate. So what you do, you use some biasing, which is to say in your simulation you artificially increase the processes that you are interested in and try then to reproduce some effective statistic. And this, for example, is a plot of effective statistic of a simulation used to achieve this plot. And in any case, you have to cope with neutrinos. And in particular, the most dangerous background for this, such an experiment is the neutrino-nucleus interaction with an electron neutrino, where you have, as a result, a high-energy electron that basically mimics what is a dark matter signal. So, in some sense, you can say that there is a neutrino floor also for this kind of experiment, because at a certain level of coupling, you have these events. And there is anyway some way to try to reduce them, reduce this background, considering that there is some difference in the kinematics of scattered electron in the processes of dark matter scattering and neutrino charge current. So you can see that due to the mass of the dark matter particles, the neutrino is the electron is always emitted in forward direction, while the neutrino event has also some large angle tail, which you can use the information to reduce the background. In any case, after all the things considered, we know that BDX expects during whole data taking 5 events of neutrino which cannot be reduced. So this is something you have to live with it, and they introduce their uncertainties in the evaluation of the reach and so on. So this is finally the reach of experiment, considering the full statistic which could be acquired in about 1 year. Again, this is not really updated to the last exclusion limit. So, for example, an A64 is now here, but still, this could be a way to achieve the exploration of the thermal target, also for the pseudo-Dirac fermion relic. And this is achieved in particular exploiting, again, the resonant annihilation that here goes from an energy corresponding to 11 GeV and to a mass corresponding to 350, which is the threshold for the detection of these particles. Okay, so since, as I said, the exit is on a proposal level, it has been approved by the Jefferson Lab, but still its future is not sure. What has been done is to build a small demonstrator, really small in mass. We are talking of 44 crystals, but using lead tungstate, which is more dense. Since we had to live with a small detector, we did it with a more dense crystals. The shielding is now tungsten, again more dense than lead. And we have 2 layers of active shielding. So we prepare with this detector, and we use it for a dark matter measurement at JLab to prove the validity of the concept and to see if there were some interesting results. So here is the situation now at JLab. You have a B dump, which is enclosed in a concrete tunnel, basically, and there is still no hole because it has not been built to place the experiment. So what was done? Well, 2 wells were dug, and the detector was lowered inside one of these wells at the level of the beam dump, intersecting the possible dark matter beam. So here I have a picture of the well with a pipe bringing all the connection of the detector. We are talking of about 7 meters from the ground level. This is the idea. So in this preliminary condition, we performed measurement at 150 microamp at 2.2 energy of a beam, and we collected what is about 20% of the BDX total statistics. And here you have a result, the exclusion limit, that of course is contained within other experiment, but it's interesting to see that due again to the resonance enhancement, it touches the curve of E137, which is a much larger experiment, which higher energy, bigger detector, and so on. So this is, I think, interesting. Okay, so we come now to what is the future and maybe the state of the art of what we can think now for beam dump experiment, which is SHIP, which is an experiment which has been proposed a few years ago and has been finally accepted by CERN. So this is an experiment that will be performed at CERN, and it is a beam dump that uses proton particles, so not electrons, and it has a larger energy, so we are talking about 400 GeV. So this is a really a multi-purpose detector, because in the concept it is beam dump, because you are making your beam impinge on what is basically a fixed target, and then you look at the product behind. But still there are several stages for the detector, and also a large, as we will see, decay chamber, and so it's a very sophisticated effort, which we will target many scenarios of physics beyond the standard model. So this is very interesting. It will be a long time effort, so we are talking of order of 10 years from now, but this is something that is can be looked now at the reference for what will be the search for this physics in the beam dump fixed target scenario of experiments. So here you have really just to have an idea list of what are the physics target of this experiment. For this lecture, we are interesting only in particular on the vector mediated dark matter, but still we are going to study really a lot of final states, which may result from a decay of many particles from the standard model. So you have neutrino portals, so possibility that dark matter is mediated by neutrino, supersymmetry, scalar mediators, and so on. So also supersymmetry particles. So really a large number, a large and broad scenario, physics scenario for this experiment. So, but now, for us, we will stick on the dark matter, in particular on the invisible, but also for the visible search for dark photons. So, as I said, this experiment will be performed at CERN, but this is not an LHC experiment because it is a fixed target experiment. Therefore, will be performed at the SPS, which is, as I maybe mentioned the lecture earlier, the pre-accelerator that accelerate protons that are then injected inside the LHC. So this is the top view of the thing. And this accelerator reaches energies up to 450 GeV in protons, and so this is what will be used for SHIP. It's not a continuous accelerator, as in the case of, for example, BDX, but it has a spill structure. So you have particular for SHIP, a structure of 7.2 spills, where you dump 2 × 10⁻³ protons on your beam dump, and then this process is repeated, and the average power of this spill extraction is ordered 2.5 megawatts. So we are talking really large power, and something that it's challenging, first of all, from an engineering point of view, because many work will be required from the point of view of radiation protection, the infrastructure, and so on. And so you see the total statistic accumulated is 5 times 10 to the 20, which is much less than BDX, for example, but you are talking about a proton beam, and this is very different, because with a proton beam you may access a series of processes to produce beyond standard model particles, such as decay of meson, for example, which are give a lot of yield in terms of dark matter particles, for example. And here is a sketch of what is the dedicated experimental facility for SHIP, which is already existing at CERN, will be dedicated completely to SHIP in the future. Okay, here I have something about the target, which is the beam dump, because they call it a target, but it's a beam dump. So it's basically a series of layers of different materials. We cannot use aluminum because now really the power dumped here is really high. It's a much more sophisticated dump, you can say. It's a total of 10 nuclear interaction length, which correspond to 120 centimeter, and it's made of layers of tungsten and an alloy called TZM, which is composed of molybdenum and tungsten, and it is the face is 30 by 30 centimeters square. So you have 13 layers of this alloy and 4 layers of tungsten, and they again are interleaved by water cooling, which is necessary to dissipate the huge power deposited in this part of the experiment. And here we have which is very interesting, the energy deposition within this target per SPS spill. So one spill of 7 seconds deposit energy that is order of almost a kilojoule per cubic centimeter inside your target. So it's something that really important. Okay, so now another thing that makes SHIP really different from a traditional beam dump experiment is that you cannot just rely on a simple shielding made of passive material, because if you produce muon, for example, with 400 GeV, you will need really many meters of lead to stop them. So you have to think of something else, and the answer is to build a magnetic shield which is able to bend this flux of muons in particular that are produced inside the target. So we are talking of order 10 to the 9 muon per spill. So you have to somehow deviate them, because otherwise they completely blind your detector and produce a lot of background. So the idea was to arrange a series of magnets, so to build some geometry that can deviate the muon from the trajectory of a detector. And here, for example, in this plot shows the top view of the muon shield in 2 colors represented the different direction of the magnetic field entering and exiting from the plane. So they had to find a way, with a bit of puzzle, to arrange a condition where with the magnet you are able to reject these muons independently from their energy, which is really something challenging, because it produces a lot of different energy muons, and you want your geometry to be effective in rejecting muons at different trajectories. You see, for example, here you have 2 trajectories that are rejected in a different way because their energies were different. So there is a first magnet which is responsible for basically dividing positive and negative muons, and then the other magnet completes, let's say, the elimination of the muons from the trajectory of the detectors, which is downstream of the shielding. So we are talking of a big object, because it's 28 meter in length and weight almost 300 tons. Here you have a 3D representation, but yeah, this is the shape that we have to produce this kind of magnetic field. Okay, so after all this part of shielding and the target itself, we have the real detector. So this is a 2-stage experiment, you can say. So you have a first part which is dedicated to neutrino physics, basically. So I won't go into detail about that. But since you produce a lot of tau neutrinos, it's a good chance to exploit this flux to study neutrinos. So you have a magnet, a spectrometer, and some emulsion to see the tracks of the products of interaction of neutrinos. And then you have what it is another challenging from an engineering point of view, part of a detector, because it is a vacuum vessel that it is used to have to give a produced particle from the dark matter or dark sector or beyond standard model scenario to decay before detecting the decay products in the detector itself, which is here. This is a really large pipe, which is almost 80 meters long, and the original idea of a collaboration was to have it with a vacuum inside, because if, for example, we have a neutrino which crosses the pipe and it interacts with something inside the pipe, gases, and produces some particles, then you will mistaken this particle, you identify this particle and think that they may come from a decay of some standard dark matter particles, while it's simply neutrino interacting inside the pipe. Now, I mean, they are a bit on the fence, because realizing such a big structure completely with vacuum inside is really complicated, because under the atmospheric pressure this thing will probably collapse under the pressure. So this is something that is still being discussed. As I said, an experiment which is being approved, but still the concept is being discussed. And to make things more complicated, you also want to veto all the possible particles that from outside enter the decay volume and decay inside this decay volume or make some interaction. So on top of everything, this pipe basically will be also surrounded by some active veto, and the idea for now is to do it with a liquid scintillator. So it will be basically a tank with a hole inside. You have a scintillator outside, and we talk about 80 meters, so we'll have to instrument all this 80 meters to be able to detect a charged particle that enters from outside and then does something that you don't want. And then finally, you have the main detector for the searches for physics beyond the standard model, which is, again, a spectrometer which does all the things that, for example, the LHBC detector we saw does. So let's say measure the momenta of the particles, measure their energy, and so on. So it is a multi-stage, you can say, detector. You have some strobe tracker, and we saw them in a second. Then basically your magnet and some timing detector, some calorimeter to measure the energy of the particles, and finally a muon detector, because muons are the only particles that survive on the detector. This is just to give you an idea of the scale, and why this experiment, so we need some time to be to be realized and put in operation, because the detector, so this is the part, for example, dedicated to the tracking and to the spectrometer for the measurement of the momenta of the particles resulting from a decay in the decay volume, it's quite large. And here you can see these that are the straw tubes responsible for the measurement of the position and impinging position of the particle. So these are really simple detector. These are tubes which have a conducting wire inside, and they are filled with gas. When a particle, charged particle, passes through one of these pipes, ionizes the gas inside, and so since there is a difference, a potential difference between the wire inside and the tube itself, you see a current, and you know that something passed there. So if you put many of them in different direction, you can reconstruct the passage of particle through them, and they are much more economic than, for example, silicon detector, such them used by LHCb or other colliders, that on this scale would be complicated to use an instrument. So this is the idea. And here you have between the two layers of these straw tube detectors, you have your magnet that bends the particle, so you are able to measure the momenta. Okay, so we come finally to our interest, main interest, which is to say what will be the discovery potential of such an experiment in the scenario that we have discussed and talked of up to now. And here is the result. So we are talking of an experiment that will be able to set limits both in the visible and invisible decay scenario, because you have this decay volume where you can have your dark photon decay and see the, for example, leptons resulting from the decay, 2 muons, for example. But also you have a detector where your dark matter particle can interact, and so you can measure, as in case of VDX, an electromagnetic shower, and therefore you can estimate a reach for both cases. I have not talked about the production mechanism of light dark matter with a proton beam. There are several possibilities, which depends, more or less relevant depending on the mass you are exploring. If you are in the light dark matter range, which is below 1 GeV, basically, the most important processes are the Bremsstrahlung of protons, so proton Bremsstrahlung. For high energy, instead, you start to have importance from the Raelian on QCD processes that happen on a quark level. So here is the reach, and you can see it covers basically all the Wien Dams experiments that I've shown before, and also moves a lot to the large masses because the energy of the beam is much larger than the one of the old Wien Damp experiment. It's interesting to know that the limit here is not due, as in the case of 37, by the fact that the coupling to fiber, you do not produce your dark photon, but it's due to the fact that the dark photon are too long-lived, they go past the detector. So still the intensity of the beams is such that you can still produce particle here. And on the other side, you have your reach in the light dark matter scenario, which is now compared to which are the most important for now experiments, which are NA64 and Bavaria. You can see that if they will be able to conclude and achieve the program that they scheduled, this experiment may be probably cover large part of the thermal target which has remained. Apart from region in low masses where, due to the fact that the mass of the dark matter has become very light, and there are some effects due to the selection trigger and the selection of events to reject the neutrino backgrounds, for example, that make you lose efficiency for this region. So that's it. Here you see this shape here is due, you see it's at about 200 MeV mass of the Chi particles, but this is taken in a scenario where the mass of the Chi particle is 1/3 of the mass of a dark photon. So in terms of dark photon, this would be a mass of 700 MeV, which is the mass of a raw meson, which is vector bosons exactly as the dark photon, and so you have a resonant production that comes from a sort of resonance that enhances your mixing, your yield of particles in correspondence of this precise mass value. So this is the result for now for a ship, and we'll see. Well, we need many years because before the experiment operates, but for sure it's one of the most challenging proposals in this field. And I'm done.
Thank you. So now is coffee break time, so we will come out with the question after the talk from Javier, and we will have time to discuss about that, okay? So thanks, Luca.